Hey everyone, thanks for joining us. My name's Namdi Regbalam. I'm a partner at Lightspeed Venture Partners, where I invest in technical tools for technical people, developer tools, AI, application infrastructure, etc. And this year I'm spinning up a new interview series where I talk to super smart researchers across various technical domains about their research agenda, some recent papers of theirs, interesting trends that they're following, etc. And for this first edition of I'm not going to call it a podcast, but let's just call it the interview series and see where it goes from there. I have with me Charlie Snell, who is a PhD candidate at UC Berkeley. Charlie and I met last year after the publication of one of his papers, which we'll talk about today. And I found his insights to be quite interesting. And even since our original conversation, he's published other research, which has been quite fascinating around some very important topics like test time scaling and in other areas. But Charlie, why don't you do your kind of brief intro and how you got into AI, and maybe share a little bit about the kind of research agenda you're most excited about.
Yeah, for sure. Thanks for having me on. Yeah, so I'm a third year PhD student at Berkeley right now. My work kind of lately has been centered around things like scaling laws with language models and reasoning and test time compute and synthetic data. Kind of those are sort of the main topic areas. I was also an undergrad at Berkeley, and I kind of got into AI a bit before that. Even I think in high school I stumbled into a Andre Karpathy blog and thought
Amazing.
it was really cool and kind of went down the rabbit hole from there. And then at Berkeley, as an undergrad, there was like a lot of opportunities to kind of get my feet into this stuff. And I've been doing it ever since. Now I'm publishing in like papers on topics that I'm really excited about. And yeah, so it's been great.
And maybe talk a little bit about the kind of topic areas you're most excited about these days from a research perspective.
Yeah. So I think right now I'm like pretty interested in this idea of using test time compute to like generate data that can then be used to improve the model itself. So I think right now we're seeing like all these interesting test time compute methods start to work very well. And so the next step is, okay, now that we have this, like what are kind of the different things we can do with it? And I think probably one of the most promising things is like this kind of offers a way to get over some of the data wall issues by like if you can use test time compute, you can get like improved outputs, and those can be put back into the model and like kind of raise the floor,
Right.
if you will. Yeah.
Yeah, I think it's especially relevant given, a lot of the conversations last year around scaling laws and are we hitting a data wall or what have you. And, there's an argument out there that, yeah, if you scope it to a narrow concept of data, like let's say just pre-existing data on the internet, we are going to exhaust that in some, deterministic amount of time. But if you kind of open up the definition of data to mean kind of synthetic data or various other kinds of things, then
Yeah.
suddenly there's all these different pockets that emerge that you can use to continue to drive those scaling laws. And I guess maybe to dive into speaking of scaling laws, maybe to dive into the first paper. So you had published a paper last year. The title was "Scaling LLM Test Time Compute Optimally Can Be More Effective Than Scaling Model Parameters." Maybe talk a little bit about the kind of like aha moments that researchers have, or like what kind of inspired them to even explore this direction and the notion of compute optimal scaling. What kind of inspired this line of thinking? What kind of brought you to this topic area?
Yeah, that's a good question. Yeah, so I guess while I was doing this work, I was kind of obsessed with two things. One is just like scaling laws in general. I really like the chinchilla paper. I think
Yeah.
like kind of the idea of like I sort of feel that like deep learning for a long time was in this stage where we didn't really have like a scientific paradigm. People would just kind of try things and then do their random evals.
Hmm.
And I sort of felt that like scaling laws kind of begins to bring us to a place where we can do more rigorous empirical study. So you can, if you have a new method, you can do a scaling law and compare it to other methods. Does the scaling improve or worsen? And so I feel like with like sort of the introduction of scaling laws, we're moving towards like a more like scientific
Hmm.
proper field. And so yeah, I was like very obsessed with the chinchilla paper. And so I think that's part of where the compute optimal idea came from. But as for like why I was working on test time compute in general, I think that part goes back to like the stuff we were talking about regarding the data wall.
Yeah.
So sort of my view on this is that like there's quite a lot of data, but it turns out that like the highest quality data is somewhat scarce. So, well, there's still a lot of high quality data, but it's definitely more scarce than all the other junk data. And so like if you train a model on like the best data, it's going to perform a lot better. It becomes this question of like, how do we sort of squeeze more generalization power out of like the very best stuff that's out there? And it sort of seems like, gradient descent, just training on this data should like intuitively be nowhere near the limit on like the amount of sort of generalization power you can squeeze out of the data. So I got interested in kind of test time compute as like a potential approach to get around this. Like if the model can sort of think more on challenging questions, it can like, with additional compute output better outputs than it normally would. And in that sense, you can think of it as like a data multiplier. So like if you sort of think in terms of standard scaling laws, like if you had enough data, you could get to like the performance of 1, but you need a lot of data. So it's not really practical. But by doing this more complex, like test time compute training process, you can squeeze that performance with less data. And then once you have that, you can, in theory at least, distill kind of the capabilities back into the model so it does it efficiently at inference time. So that was sort of my thesis, was like, okay, this test time compute direction is very interesting. Let's explore that. And I was also kind of obsessed with scaling laws. And so I kind of married these two together when working on this. Yeah.
And so in effect, by leveraging these techniques, you sort of change the slope of the scaling law.
Yeah, I think there's a way to view. I mean, it's unclear if you're changing the slope or just the intercept. I think that's an open question, but I think if you change the slope, that's potentially a bigger deal. But
yeah, that would be amazing. But yeah, I hear what you're saying. And then maybe just for the sake of listeners, like when we say compute optimal, maybe just like define that term and what you mean by that.
Yeah. So I guess I'll go back to the Chinchilla paper to give kind of the background. So the paper is called, I don't know the exact title off my head, but it's something like Training Compute Optimal Language Models or something. And basically they introduced this concept of compute optimality. So like you have your pre-training loss is a function of how many parameters your model has and how much data you train it on. So you'll get to some loss. And then the amount of compute you spend is also a function of those two variables. So pre-training compute is 6 times number of parameters times amount of data. Then we can kind of do an optimization problem. Given this compute budget, what is the optimal way I can allocate these two? That's sort of the pitch in the Chinchilla paper. I was exploring different ways of using test time compute, and it was kind of becoming clear that, in certain settings, different approaches worked better than others. So I thought that like there was sort of a very natural parallel here, which is like, okay, we can, depending on the question we're given, we might want to allocate compute in different ways. And so this brings up the question of like, what is the best way to allocate it? And so we can vary different axes. In this case, it looks a little bit different than parameters and data, and it's instead like parameters of your search algorithm. How many beams do you use in your beam search? How many times do you let the model revise its answer? Stuff like that. Yeah. But you can, cast an optimization problem over these parameters and for a given test question and find kind of this compute optimal idea. Yeah.
That's great. And the questions, I thought this was really interesting, right? Because to your point, the sort of like the kind of decision variable in some sense you're using in the paper is the difficulty of the question.
Yeah.
Which is interesting, right? Because, you can imagine scenarios where you may not a priori know what the difficulty of the question is. Yeah. Maybe talk about some of the nuances there. Like maybe one, how do you arrive at question difficulty as being like the key metric? And then like, how does one calculate that in practice?
Yeah, that's a good question. So in sort of the general form of compute optimal scaling that we define in the paper, it doesn't necessarily have to be in terms of question difficulty. So like if you come up with something more clever, you can plug that in.
Sure.
We found that like in practice, for the purposes of our analysis, question difficulty is like pretty correlated with how the different test time compute strategies behave. How I kind of arrived at this was more like when I was testing things, one sort of thing I was constantly looking at was like, there were certain questions where like they were just very easy. And so kind of no matter what you did well. And so I kind of became more interested in these harder questions where like if I ran beam search, suddenly it worked, but the more trivial things weren't working. So I was kind of like during my analysis process, like binning things by difficulty, and we saw all these trends pop out. So in reality, you could use any kind of statistic to do your compute optimality, but when we were doing our analysis, this notion of difficulty became like a pretty useful one. And as for like measuring difficulty, I agree that it's like if you're just given the question, it's a little hard. There's a paper that came out after mine that showed that like you can kind of predict difficulty just given the question and it works reasonably well. But I think in general, like there could be some deceptively easy looking question, which is actually very, very hard. And I think
Yeah.
like this isn't too uncommon. So
Yeah, totally. But as like as sort of like a proxy for what you're trying to get at, which is some notion of how much compute should I apply to different problems, this question difficulty thing works, reasonably well. And I think in the paper you sort of call it almost like a sufficient statistic. For this, which I always love that expression because I'm a big economics nerd, and a lot of economics papers will talk about something being a sufficient statistic. So that always lights me up. But that makes sense, and it has some like intuitive appeal to it. Like, it's like if you're taking an exam, ideally you can kind of read the question and get a sense of how hard they are and allocate your budget, accordingly. And it's sort of similar here.
Yeah, exactly. And I guess I can explain how we compute it too. Basically, the way we did it in the paper is a little bit impractical, but it was mostly for analysis purposes. But how we do it, we sample a bunch of outputs for a given question and measure the rate at which it gets the correctness. So that's what we call oracle
Right.
difficulty. So in that case, we're using the true answer, so it's not practical. We also have another one called predicted difficulty, where we use a verifier on all those outputs to get a score.
And that was one of the nuances I wanted to ask you about, because there's sort of like doing this for analysis purposes, and then there's like, hey, if I wanted to use this in practice in like a online context where I don't necessarily have the oracle answers, I mean, I even have a verifier. Can this question difficulty thing still apply there, or do you need essentially some signal to figure that out?
Yeah, I think it can apply. So there was this paper that studies this question of like, can you just train a model to directly predict the difficulty and then use that to route certain decisions? And they found it works like fairly well. So I think there's absolutely a practical use case. Definitely usable, yeah.
It kind of reminds me of like in the RL context, like training a reward model. It's sort of similar.
Yes. And I think there's definitely some connections to like RL in terms of exploration. So it's like you might have to gauge the situation to decide like how much you should explore versus exploit. So like I think this idea of like compute optimal, test time compute depending on the question, kind of related to that. Yeah.
Yeah, and I guess in this context, it's more of a cost model than a reward model. It's sort of like, how much is this going to cost me to solve this problem?
Exactly.
It's essentially equal across questions, but how much is it going to cost me in terms of compute?
Yeah, exactly. Yeah.
I thought that, one of the most striking things, and it was part of the reason I had reached out to you after you published this last year, was just like the efficiency gains of this kind of method. And maybe one way of thinking about that is like a smaller model that uses this method, versus, a larger or more long pre-trained, model, and how much better this approach can be. So can you maybe talk about that and get into some of the trade-offs between this versus pre-training?
Yeah. So in the paper, we did some analysis comparing to like a small model with test time compute versus a 14 times larger model with just, no extra test time compute, just one chain of thought. And to give some background is like, if you train the larger model, you're going to spend more compute pre-training it, but you're not doing test time compute, so it's a little cheaper. Versus the small model, you're going to spend less compute training it, but then each inference is going to be like a little bit extra. It has less parameters, so that kind of helps a little bit, but there's still like a good cost from doing the extra test time compute. And then another relevant variable is like, if I'm going to deploy these models, how much inference am I going to do? So if I'm Google and I'm deploying this to like billions of users, there's going to be so many requests that if each one is using, 60 times more compute at test time, that's really going to add up. it's going to exceed the pre-training budget. But if I'm just a researcher or a small startup and I'm deploying to a smaller set of users, the inference compute will likely be much less than pre-training, so we can get away with more. So yeah, we looked at this question of like, if we do kind of all this math, depending on our inference ratio, depending on like how much bigger the model is, can it be preferable to just use a smaller model with extra test time compute? I guess I should caveat this by like in the paper, we study like a couple different methods of scaling test time compute. And depending on, how you do the test time scaling, you might see different results. But with the methods that we used, what we found was like on the easier questions, there's definitely a preference towards, and again, these are easy questions in the math data set, which are like still a little challenging.
Okay.
But on the easiest questions, like there's a preference towards using the smaller model plus test time compute over scaling parameters. And then on the medium questions, like medium difficulty bins, we find that like if you don't have too large of a inference requirement, it can be preferable to scale test time compute. But if you're like deploying to 1 billion users, you might want to just pre-train more. And then on the very hardest questions, we found that the methods we used for scaling test time compute kind of didn't perform too well. And in those cases, it is like preferable to pre-train. So definitely varies case by case, but there's definitely some situations where there's like a pretty like good gain from test time compute. Yeah.
And my understanding from the paper that as far as like the different methods of scaling test time compute that you kind of evaluated here, it was the kind of sequential iteration that generally performed best. Is that right?
Yeah, the sequential iteration was showing the strongest results. So we did like search against a verifier with like some tree search. And then we did this thing where we trained the model to revise its answers in context. And that one did show stronger trends in general.
Is this the chart, right? That with the
chart
between pre-training and test time. And so you have the difficulty level on the y-axis, and then I guess the x-axis here is sort of, what is this? Could you explain?
The x-axis here is like the amount of inference you're doing. So if you're generating more outputs to like help you figure out the best answer. Basically, the thing we're comparing here is the stars represent the larger model's performance within each difficulty bin.
Mm-hmm.
And we place the stars at different locations on the x-axis because depending on how much inference we're going to be using with the model, the point where it is comparable kind of shifts. So I think the rightmost like dashed line corresponds to like there being like very little inference, and the leftmost is if there's like a ton of inference being done. So what we're comparing here is like if the line is above the stars, that means that it's preferable to use test time compute. And if the line is below the stars, then it's preferable to scale parameters. And you see there is kind of a shift where like the easier questions, especially in the revision setting, so that would be like bins level 1 and 2, show improvement over the stars. But then as we go down toward the harder questions, it kind of phase transitions.
Yeah, it makes sense. And I think I misspoke earlier. The y-axis is the accuracy, so it's sort of the inverse of the difficulty.
Yeah. The y-axis, the axis is the accuracy, and then we have the difficulty bins as sort of like these different colors.
Mm-hmm. Yeah, very cool. As folks are kind of just thinking about these results, I mean, the whole kind of supposition here is that one may want to think about this trade-off between, pre-training and test time compute. I guess maybe just to kind of poke at that a little bit, as a researcher, like how often do you think in practice, and maybe this will evolve in the future, but in practice that's actually something that people will trade off? By which I mean, there are some people that will do a lot of pre-training. There's some people that only do inference and never do pre-training to begin with. So it's sort of like a weird question to ask in a certain sense. But like, as you sort of pose that, like, do you think it's a realistic thing that people will trade these things off in some sense?
Yeah, that's a good question. I think like realistically, the findings here can kind of inform, at least like, I think this kind of analysis should be done more and can kind of inform some of the modeling decisions made. So if Llama is going to make another model, should it be a smaller one that's really good at test time compute or a really large one? And this can like, inform some of those decisions, and they would probably conduct their own analysis, but this is like showing a way to do that. So I think you're right that like different entities will maybe be doing more of one versus the other, or may only be doing one or the other. But for the purposes of like sharing the best models, having the models that, get the most use, you might want to consider these things before you put them out there. There's definitely some utility there. Yeah.
Yeah. And maybe just lastly on this paper before we move to the second one, as you think about just like stepping back and thinking about inference scaling, test time scaling, et cetera, any kind of like forecasts about how this will affect the future of LLM development? I mean, some of it's probably along the lines that you were just sort of alluding to, but any other sort of implications that you're thinking about?
Yeah. So I think, I mean, in the recent months, especially like in the months after this paper came out, there's been a lot of development in test time scaling with like the O1, O3 models and like the R1 model. And they're showing very strong results, at least on these math and science and coding questions from scaling test time compute. And I guess I would expect like there's probably a lot more juice to squeeze out, but it does seem like there's a few open questions that haven't been answered about like where this stuff is going. So one is like, how well do these test time compute methods transfer to other domains? So
Um,
in our paper, we explored math. The reasoning models that are out there are pretty good at math and coding, but not necessarily as good as at other things. So do these techniques, like, can they also provide a lift to other things that aren't based on like objective answers where it's easy to grade and check? Can it also help with like creative writing or something like that? I think that's an open question. And I think potentially has a lot of implications for like how far this stuff ends up going. And the other one is like, if we scale the sort of base model and the test time compute training, how do these things stack essentially? I think that question is not answered. So maybe if the base model is like, twice as good, the test time compute is like 10 times better, or maybe it's
yeah.
only a little bit better. I
Are there
think
like
it's
interaction
unclear.
effects?
Yeah, the interaction
Yeah.
effects between these two. I think it's unclear, and like I think that's an important question, like help kind of project out the future capabilities of these models as well. Yeah.
Yeah. I mean, intuitively, I feel like they're probably, I'll put it this way. I wouldn't assign a high probability to the interactions being zero. It's sort of a question of like how much they are
Yeah.
or how large they are. Intuitively, or at least kind of from my read of the research, it seems like these, whether it's reasoning or some of these other things, at least they tend to come from the larger models, at least more reliably. And so you might expect some interaction there. But yeah, I mean, I went to, NeurIPS in December. I asked everybody I met what they thought about O1 and test time scaling and whatnot. And I think one of the interesting thing was like to your point around the domain specificity, in these areas where there's like precise answers that you can get to, whether it's math or coding or whatever. My sense, or at least the sense from like a lot of people I spoke to, was that a lot of the large labs are quite good at collecting large amounts of that kind of data. But in other domains where the verifiers or what have you are just fuzzier in nature, I think these are just like naturally areas where the big labs may not be as well suited to collect large amounts of that information and might be better suited for people in industry, like other industries I should say, who are close to the domain specific data and understand the problem spaces very well. It may be an interesting area where like people outside of the big labs can kind of contribute to this in a major way and maybe even be advantaged when it comes
Yeah,
to
yeah.
test time scaling.
Yeah, that makes sense. Like figuring out other things that we can like easily measure and optimize against, potentially very big. I mean, I think it's also just the case that like, I mean, not just the labs are good at these things, but they're also just easier to optimize against, I think, in some sense.
That's right. Yeah, no, that's right. Would love to talk about second paper. This was one that you also published last year. This one's called Predicting Emergent Capabilities by Fine-Tuning, which I thought was really, really interesting. And my read of some of what you're getting at in this paper is sort of like, we know there are these emerging capabilities that come out of these models, as we scale them up. But, unlike the kind of pre-training loss, which you can kind of plot on like a nice curve, and it's a very predictable thing, we know that, if you apply this much compute, you get to these sorts of performance capabilities at the kind of pre-training level. These emergent capabilities are somewhat fuzzier and harder to forecast. We know that they do pop up as you scale these models up, but it's harder to say sort of before a model kind of has this emergent capability, with how much more compute needs to be applied before it kind of has that thing.
Yeah.
And, there's some of our discussions about, pre-training and how these big labs are thinking about that. It would be really nice if you could kind of tell in advance when these things were going to come, or even kind of like pull them forward in the process. And so maybe talk about the insight here around fine-tuning and how you kind of came to that as a way of kind of predicting emergence.
Yeah, I think this was kind of an interesting like research exploration where one of my friends had pre-trained these models and we had all these checkpoints. So I had been kind of like playing with them, evaluating the different checkpoints, looking at trends, and I found all these evals where like there's very clear emergence. So I had this previous paper called like the false promise of imitating proprietary language models, where we found like if you do sort of this broad instruction tuning distillation from a larger model, it improves the style of the weaker model, but not really the capabilities. But if you do like a specific task, you can improve the capabilities. So I like kind of had this paper that I had previously done in mind, and I was looking at these checkpoints. I was really curious, like, okay, if I fine tune for these tasks, what is going to happen to this emergence curve? I had no idea and was just really curious. And so I ran the experiments, and like it was very interesting. It just shifted the curve, and also found that like as you vary the amount of data, it shifts the curve more if you train on more data. So once I found this trend, I was really excited. I was like, wow, this is really fascinating. We can potentially use this to make predictions about these capabilities. So that it kind of just went from there.
And when you say shifting the curve, could you almost like visualize that for us? Or maybe I can like pull up the...
Yeah, that's a good example. So you see like the stars are like the few shot performance, but then once we fine tune, as we vary the amount of data, the kind of elbow gets shifted. Yeah, it's pretty interesting, and it's very systematic. So like if you go back too far, it's still going to be flat, but then suddenly it pops up. And yeah, so there's something strange here. I think in general, fine tuning isn't that well understood. Like it's kind of a strange thing that you can spend a little bit of data and like get the model to like do something interesting with it and be so efficient about it. And so like I don't think it's like super obvious or even known like what's going on here when like suddenly the fine tuning works, but it doesn't. But it didn't, with the weaker model. But like if I were to guess, there's like some sort of fusion or interaction effects with like the base model and the fine tuning, where like the capability is like kind of there in the base model, but once you have a little extra fine tuning, you kind of strengthen it and elicit it to where it like starts to work. Yeah.
One just clarifying question, like when we say we're talking about emerging capabilities and fine tuning, did capabilities emerge during fine tuning?
Yeah, so the capabilities emerge during both pre-training and fine tuning. So if you look at the stars on this graph, these are different. So each star is different model checkpoint.
Yep.
And so as we go to the right, we're getting like more and more capability, or we're pre-training more and more essentially, using more compute. And we see that like it's basically at zero for a long time. And then once we cross a threshold, it starts increasing. And so like if you're in that zero regime, you have no way really of knowing when you're going to start increasing.
Right.
And that makes it really hard to like make forecasts or like make decisions on the basis of like, should we keep, scaling or not? So the interesting thing is like once we fine tune, we see the same kind of curve where it's like, it shifted up a little bit, but it's like flat, and then it starts to improve. And yeah, so the fine tuning also shows emergent, but now it's shifted to the left. So now we can kind of make some predictions because it's moved into the zero the region where it would be zeros in the few shot setting. So,
and in this topmost line, I guess you're only showing it up. I guess you're not showing the left part of this. So it was flat before that.
Yeah, it was flat before that.
And so the fine tuning kind of pulls the point of emergence sooner. But are you in fact predicting that point of emergence, or you just know it's going to happen sooner?
Yeah. So in the paper, we set up these sort of scaling laws to like actually predict when that jump will occur in the few shot setting. So we can get like a very concrete prediction. Yeah, basically like we have sort of a functional form like this, which is a function of like how much fine-tuning data you have. And it models like, depending on how much data you have, where will the emergence show up? And then we can fit this sort of function from a bunch of fine-tuning runs on different data amounts, and then we can sort of take a limit under this function to like sort of the low data limit. So if we were in the few shot setting, where would it show up? And doing this, we found like can give like pretty reasonable predictions. It depends a little bit on like how far in advance you're making the prediction. But like across 4 different tasks, we found that we were able to make some interesting predictions.
Yeah, I'm always just fascinated by the kind of like ubiquity of these like power law,
Yeah.
like functional forms. Like, did you expect that? I'm sure you tried different things, or do you even have any sense of like why these things seem to pop up in so many places? And again, there's sort of analogies to economics theory. It's very similar in that
Yeah.
term as well. You have these kind of like power law formulations.
Yeah, it's a good question. I don't think I have too much insight here. So I did try a couple other things, and this seemed to be the most natural fit to the data. It is kind of interesting that like we see these power laws a lot. I think it seems like it's like a simple form that works well. I'm not sure entirely why they're like showing up everywhere.
That makes sense. Is it fair to say that, different tasks or different emergent capabilities have different levels of kind of predictability?
Yeah, so that's kind of what we found in the paper.
Yeah.
And this there's some confounders. So it's unclear if it's fundamentally about the task or the data. I'd say the general procedure we had could be like more robust, I think, in general. So what we found is like if you do more fine-tuning runs, you'll get a better fit. But I have to stop at some point. I can only run so many. And maybe depending on the eval, it might be more noisy than others. Like there's all these effects which might kind of make it harder, easier to predict, but it's plausible that like in sort of the limit where you can run arbitrary amounts of fine-tuning runs to get these predictions, like maybe you would get similar predictability, maybe you wouldn't. But I think it's unclear whether it's the task or other things.
Yeah, benchmarking and kind of evals are always tough because we're calling this a task and we're measuring it with a particular benchmark. But that benchmark is just data. We could have had a different set of data and called that the same task, and the performance will be slightly different.
Yeah.
It's like it's not obvious which is the right one, or if either one is more right than the other. It's also tricky, I think, going back to the power law thing, because I just nerd out on this kind of stuff, and like fitting these curves is very sensitive to noise, like in the data.
Yeah.
Like the slope can change, and these are orders of magnitude, so that's like a very different, you end up in a very different place. So yeah, it could be worth exploring, but
Yeah. So I mean, one thing we did in the paper was like that I think is not done enough in like scaling law stuff is like trying to estimate uncertainty of like the parameters of the scaling law. So there's various ways to do this, but I think in general it's a good practice. That way you can get some error bars. Like the curve could be this or it could be this, I think, and that's kind of like a robust way to report things. Yeah.
Yeah. And then I guess speaking of robustness, like in this emergence prediction, what are other things worth exploring in terms of making this more robust, more kind of reliable as a method for predicting emergence?
I think the big thing comes down to like figuring out for a given task, depending on like how much noise there is in the eval, how many fine-tuning runs do you need? And can you like do this a little more systematically? I think that would be huge for making this more robust. Yeah.
Basically, if you want the error bars to be a certain max width, how many?
Yeah. And there's a question of like what fine-tuning runs do you get? Like how much data, how close together do the model checkpoints need to be? So I think there's various factors like this that are worth looking into. Yeah.
I remember last year there was that, I don't know if it was a blog post or like a proper paper that Anthropic published on like error bars basically in the context of evals and this was like, this generated such controversy because people were like, oh, this is not really research.
Yeah.
This is not, we know this is like basic stats.
Yeah.
I don't know. I'm sort of like whatever encourages good behavior, I'm sort of fine with. I mean, the number of papers that have been published on like p-values, which you think would be like a known thing at this point.
Yeah. It is true that like this stuff isn't used enough in the field. I think uncertainty isn't thought about like enough. So it's definitely good to like bring these issues up. Yeah.
Yeah, especially because, there's a lot of uncertainty. There's a lot of experiments that are run before you run like the final thing.
Yeah.
There's like a whole bunch of these things that in a normal in a more rigorous like scientific context, you want to like factor in some sense. But
Yeah.
maybe just to wrap up, just things you're thinking about this year, maybe upcoming papers.
I'm interested in sort of this idea of now that we have good test time compute, what are kind of the interesting things we can do with it? And so one was kind of a thing I was talking about earlier, like we can like use it to distill outputs back into the model and sort of trying to understand what that means, what kind of the limits of that are and things like that. And then I've got other projects going and like other use cases of test time compute. I won't say too much about them now, but they'll come out soon.
You want to give us a scoop?
It'll come out very soon.
Go
I
ahead.
think there's a lot of exciting stuff to do now that like sort of the paradigm is like shifted a little bit away from just pre-training and now there's this other thing. So there's a lot of exciting stuff to do, I think. Yeah.
Yeah, I think that's right. I mean, I think it's why I'm so excited about it. I think it really opens up the field and makes it much more accessible to kind of contribute to the latest and greatest, research here. Because it's a lot less compute that we're talking about in this kind of post-training paradigm typically, and so in test time scaling. So I'm excited. Thank you so much for doing this, Charlie. Appreciate it. And
Yeah. This was really fun.
yeah, and if and in the future, like you have like a paper coming up and you want to give us the exclusive, like I'm happy to be the first to report on it. But also, man, yeah, thank you so much.
Thank you very much. This was really fun.